Welcome in the presentation of the FeatTS, feature-based time series clustering. FeatTS semi-supervised algorithm that uses the features extracted from the time series in order to cluster them. To the best of our knowledge, FeatTS is the first feature-based semi-supervised clustering framework with these key properties. FeatTS is based on clustering by seeding concept. The idea is to create two kinds of connections between the data of the dataset, called must link and cannot link. With the must link we are defining a constraint of belonging between the two data. It means that two data points should be clustered together. By opposite, the cannot link defines a non-belonging constraint, hence going to separate the data points. Seeded k-means is the most prominent algorithm of this category. We also compare FeatTS against the state-of-the-art of the unsupervised time series clustering called K-shape. K-shape computes the most representative time series in a given cluster and inserts in that cluster all the time series that are similar to the most representative one. The main problem of K-shape is that it assigns spurious time series to clusters and it does not deal with time series of different lengths. In this figure we can see the 5 main steps of our algorithm. The first step is the extraction of the features. Indeed, using a library called tsFresh, we can extract numerous features. In fact, as indicated in the figure, we can extract plenty of features completely different. Among all the features extracted, only some of them are really useful in order to obtain good performance. Therefore, we need a method that permits to discriminate which features have the best correlation with the dataset. The operation of discrimination of the features is done via a procedure called Benjamin and Yacatelli procedure. This procedure needs a small subset of supervised data, in order to compute the p-value for each feature useful for considering the importance of each of them. In the figure, we can see how the quantile feature is the most discriminative according to the Benjamin and Yacatelli procedure. However, this procedure doesn't let isolate the number of features useful for clustering. Therefore, in order to obtain the optimal subset of features, FeatTS adopts an algorithm called principal feature analysis. PFA computes the explained variance of each feature and, based on a set threshold, selects the minimum number of features that need to obtain the threshold requested. In the figure, we can see that fixing a threshold equal to 90% of the explained variance, this can already be obtained with the first 3 features of the left-hand table. Therefore, only the first 3 features will be used by the algorithm from now on. Once we select the features, we convert the time series and their relationships into edge-weighted graphs. The encoding of time series into edge-weighted graphs allows us to capture the global relationships among the raw time series samples. Therefore, we convert each time series in an edge-weighted graph where the vertices represent the time series while the edges represent the distance between the connected nodes of the edge, i.e. the difference between the values of the feature of 2 different time series. In the figure we can see that the weight between V1 and V2 is 14 because of the difference between the quantile features of time series 1 and time series 2. In order to capture the similarity, we only retain in the graphs the edges whose weight are less than a given threshold distance. Therefore, once ordered in ascending way all the distances and select a threshold, FeatTS cuts all the edges with the distances higher than the maximum fixed. In the figure we decide to keep the 50% of edges, so all the edges with a distance higher than 28 will be removed from the graph. Finally, once pruned the graph we will apply an algorithm of community detection in order to extract the communities from the graph. Feats apply this routine on all the graphs obtained by the features. Therefore, we need a structure to combine all the results obtained in one single data structure. FeatTS uses a structure called Co-Occurrence matrix to combine all the communities in one single structure. The Co-Occurrence matrix is a matrix where the columns and rows represent all the time series of the dataset, and each cell represents a similarity value between these time series. The similarity of 2 time series increases with the number of times the 2 time series are clustered together. In order to make more robust the computation of the similarity, each feature has weights that depend by the number of communities found by the community detection algorithm. The weight will be computed dividing the number of communities of the features by the number of requested clusters if the number of communities is higher than the number of clusters. Vice versa, if the number of requested clusters is higher than the number of communities extracted, we invert the numerator and denominator of the function. The weight is equal to 1 in case the two values are equal. As an example, here we show the weights of the three chosen features corresponding to the number of communities found in each graph encoding of the respective features. Indeed, the algorithm for community detection finds for the trend STD error 3 different communities. In this case we have divided 2 by the number of the extracted communities, i.e. 3. In the other feature, called trend_r value, only one community is found, thus we divide 1 by 2. Once we have computed the co-occurrence matrix, we can apply the k-medoid clustering algorithm on the matrix in order to extract the corresponding clusters. In order to evaluate the performance of our algorithm, we first used the datasets of the UCR collection. This collection consists of about 64 datasets. In the figure we show an excerpt of the results obtained on the datasets. We can see how the results obtained by our algorithm, which are expressed through the adjusted mutual information, exceed those of seeded k-means, used as a baseline, and k-shape for the majority of the datasets at hand. The second dataset is a real dataset that was provided to us by the Georges Pompidou Hospital in Paris. The latter consists of patients who suffer from kidney disease and for whom we need to predict whether they need dialysis or not. We have two variants of dataset, whose difference lies in the number of patients per dataset and the length of the measurement. We can see how the results obtained by our algorithm outperform those of seeded k-means. We can't test k-shape on this algorithm because it contains time series with different length and k-shape doesn't handle this kind of dataset. Finally, we tested the scalability in terms of time of FeatTS, increasing the size of the dataset with the fixed length of the time series and increasing the length of the time series but leaving the same number of time series. We can see how if we increase the number of time series, the time, expressed in log scale, clearly increases. Moreover, we can see that the majority of the time is spent for the creation of the co-occurrence matrix. The situation is somehow opposite when we increase the length of the time series. In that case most of the time is spent to extract the features from the time series. We have presented FeatTS, a system capable of doing time series clustering while leveraging custom features for each dataset that best fit the dataset itself. This overcomes the results in state-of-the-art algorithms relying on raw data or on a fixed set of features. In the next future we plan to make the pipeline completely unsupervised, and we also want to be able to set a dynamic threshold to be used in the graph encoding. Finally, we are evaluating if the use of relevance weights extracted from the supervised procedure can be used in combination with the current weights. Let's present FeatTS with two main scenarios. In all the scenarios we will use the kidney dataset as example. For this scenario, we want to keep the 80% of the distances for each feature that will be found. Moreover, we want to use only the 20% of all the labels provided by the dataset. We choose the number of clusters we want to obtain and the dataset. In this view, it is possible to see the time series provided in input from the dataset. Each time series will be shown in the chart on the right. Moreover, it will also be possible to select multiple time series to be visualized at the same time. In the next view, the system will select the most relevant features according to the selected parameters. For each feature, we will display the graph extracted from the features and the communities detected. Moreover, will be shown the main information of the feature selected, such as the weight, the number of communities, and the maximum distance of the threshold. Finally, we are going to display the final clusters of the time series. It is possible to view in the chart all the time series that belong to the cluster. The black time series of the chart represent the original time series of the dataset. The id of the time series that belongs to that clusters is visible in the chart legend. Red time series presents in the chart represent the median time series of all the time series belonging to that cluster. The computation of the median of the time series is an excellent way to visualize the average trend of the time series of a given cluster. Moreover, by comparing the medians of each cluster, it can also assess the difference in trends between the various clusters. In the second scenario, we want to personalize the distance threshold of one particular feature. In the selection of parameters view, there is a slider that allows to choose the percentage of distances to be kept for each extracted feature. This operation could exclude some distances that in some features are important to determine some global relationships. Thus, by performing the same procedures seen in scenario 1, we arrive at the visualization of the features and the extracted graphs. Pressing the Change Threshold button, we can see all the distances calculated for that particular feature. In red will be displayed the distances that have been accepted by the threshold inserted in the first step, while in black are the distances that have not been accepted. Changing the distances for a single feature is sufficient to select any point and select OK on the alert output. We can see how, by reducing the distance, the number of communities for that feature are increased. This is very useful when the user wants to increase the number of clusters. In fact, reducing the distance threshold provides more communities and therefore a more accurate result in the final clusters. Thanks for your attention.